Great. Well, thank you, Magnus, and Alan as well. Thank you for having me at Cloudburst. It's a great opportunity to speak about some things that I'm really passionate about to do with large-scale data processing and how you can do them all on Windows Azure, even though some of those things are non-Microsoft technologies and are things that might otherwise be kind of scary to look at, like Java estates. It's going to be quite a lot of hand waving when it comes to Java because it's kind of scary, but hey, it's only a couple of screenshots and we'll get past them pretty quickly. But first of all, let's use social media to our advantage. Tell everyone how great I am on the hashtag Cloudburst and follow me if you fancy. I'm Andy Wareweb on Twitter. So let's set the scene, shall we? Data, getting value from data at large scales is more of a challenge than it probably should be. And there are lots of different propositions, and some of those I'm going to show you today from three main divisions of data processing technologies on Windows Azure. Now, when I say on Windows Azure, I mean that these can be deployed to Windows Azure, you can run them on Windows Azure, but they're not actually made by Microsoft. None of these technologies are Microsoft technologies. They're all open source technologies, which has its own sort of challenges alongside it. And I just wanted to sort of let you know right up front that you're going to have to face some tough technical choices if you're going to go down these routes. So you might have to start looking at your data as something that you can read effectively and traverse effectively, but you can't necessarily update it very easily. It's something that if you have petabytes of data, there's no way you can go through every single one of those and say, update that to append some more information in there. It's a very tricky thing to do. So the technology state of play today is that we tend to look at read traversal as more valuable than the writes, the updates, the delete traversal. So that means that we can do things very quickly on reading, aggregating information, but if you want to update afterwards, we probably don't have the greatest solution for that. And that's indicative of the entire industry as opposed to any limitation of Windows Azure. We also have the challenge that these estates are hybrid rather than homogeneous. So that means that we have the ability to run things with C#, but underneath it we're running Java. So we have the difficulty of managing a Java ecosystem at the same time as running our own language variants on top of that. And you have to embrace that, and the cloud actually helps for quite a few reasons, one of which is that rather than provisioning clusters of Linux nodes or something like this, which we might not be comfortable with managing, and looking after them for like months on end, with the cloud we can provision them for, say, an hour while we run a query, and then deprovision them, taking away our management overhead. We also need to establish some alternative skill sets that aren't just the standard .NET and SQL Server skill sets. We're going to have to find ways of augmenting these different hybrid estates with our existing skills, making our skills valuable and relevant again. And we also need to find ways of taking everything we've learned about writing technologies for Microsoft platforms and apply them in this new world. So everything from unit testing all the way through to continuous delivery and that sort of idea needs to also be brought in when we move to these new technologies. We can't just abandon everything we've learned about software engineering on the way. Okay, but why would we do it? Bravery leads to rewards. There's not going to be many more of these slides, which are just bullet points, by the way, but I want to get them out of the way to start. With data, there's massive value held in repositories of clickstream analytics all the way through to sensor data that's been collected about you at all points in time. Now, the people who are going to be the next Twitter, the next Facebook, will be embracing the same things that Twitter and Facebook do, which are these huge repositories of data which can be mined for valuable information about individuals. That is how these companies have become incredibly valuable. They suggest links between people and information points. And by doing that, they've established themselves as huge companies, and they can say that my data is actually where my value is. The people who come after them, because no tech company lasts forever, well, some maybe will. Hopefully Microsoft will be around a bit longer, but none of these consumer-based companies has got necessarily the longest lifetime ever. The people who come after them, people who work with them in the future, are going to understand the same things about data value. There's this idea that I like to talk about, and I've got a slide about it later, so I won't harp on too much right now, but I call it the commoditized query. It's about the perfect query, the perfect cloud-based query, how you can get value without actually having any of the constraints that you previously had. There are new types of technology out there where you can start modeling your data around what it means rather than how you perceive you had to store it. So rather than thinking tables, and rather than thinking views, and rather than thinking about stored procedures, which are all technology things, what we really want to do is have our data expressed in such a way that it sort of matches with our cognitive process. So we sort of say data point links to other data point, links to other data point. That's how our brains work. We don't actually have tables in our minds. We have my friend relates to my other friend, relates to some clothes because of what I've seen them in the past. It's a cognitive process of traversing relationships between nodes. And I'll get onto a technology which allows us to do that later on. And just one real thing is to say is that none of the technologies that we understand now are necessarily completely obsolete, and none of them are irrelevant or invalid. The things that are irrelevant and invalid are the constraints on scale which don't apply to this technology space. You can't do everything with yesterday's technology. It doesn't scale to the level we need. If we've got a petabyte of information, we can't put it in certain databases. It simply won't work. So instead, we have to think about what we can do instead and get rid of the constraints, but still take with us all the things we've learned, all the value we've built up in our careers and in our businesses. So big data, okay. Hands up, who's heard of big data? Who's had a consultant come to them and go, big data is this, that, and everything's big data, and nothing's big data, and everything's big data, and done a lot of hand waving and not really explained anything? Okay. So what I want to sort of show is that actually there are answers to the big data questions. There are ways that Microsoft are becoming relevant in this space, because I don't think they necessarily were a few years ago. My talk is going to be about big data processing. It's not going to be about data science. And we'll go and do a little bit of history at the moment, but I just wanted to bring out one joke. I only have one joke about data science, and it's particularly relevant after Scott's talk. What's a data scientist's favorite language? R. Yeah, there's a language called R that data scientists use. Yeah, okay. There, cheers, man, cheers. Okay, so let's go a little bit of the history of it then. So, IBM, they've been doing big data for a long time, but really what big data to them means is huge punch cards. That's a bit of a silly play, really, but I sort of imagine that what they do these days when they talk about big data, because they like to talk about it a lot and making the world better through big data, but they never actually do anything. So what I like to think of what they do is they just print out all their old Fortran cards, but really, really, really big, and go, that's my big data there. So that might be the output. Anyway, really, it's not that much different now. What we used to have were paper-based mechanisms, card-based mechanisms for input-output. And we were limited by our ability to marshal that data through systems. So we had to shine light through punch cards and detect whether light was coming out, and that would make electrons zap round, and that was your program, and then that was also your data. And that's great, but then you have to have this physical media actually sort of going through a machine, or someone's plugging it in and pulling it out and all that sort of stuff. And it really took people sitting there and doing this stuff and marshalling paper through things and not being able to make it go any faster than 20 miles an hour, because if they did, it would set fire to the card and then you lose all your data and it wouldn't necessarily feel that good. So we haven't really got much beyond that, because we still have the same fundamental problem, and that is that our ability to do analytics over huge amounts of data is limited by our ability to deliver that data to the machines which are doing that analytic calculation. Now, what the industry has done to solve that is something called distributed file systems and data locality, and it's something which is core to how Hadoop works. The machine which is doing the calculation also stores the data on its own hard drive, so that it doesn't have to then go over the network all the time to get data. It moves it a lot closer. In the cloud, we have a slightly different take on that, where we actually have a network backbone which is so high throughput that we don't have to do that so much. But this was a genuine industry-changing idea which came out of the Google white papers from the 2000s, early 2000s, and from that was born Hadoop, the distributed file system, the ability to take a job, break it into smaller tasks, and pass it around a cluster. Okay, now, SQL Server. Ah, dear, it's always sort of the elephant in the room when you start talking about things from the other side. When you're not talking about Hadoop. If you're talking about SQL Server, usually Hadoop is the elephant in the room. When you're talking about Hadoop, SQL Server is like the elephant in the room. One thing to say about SQL is it's very, very performant on small sets. It does lots of stuff that Scott just spoke about, which are actually quite impressive, but it has failings when it gets to a larger size. Now that is primarily because it's an old database technology. It's designed on tables, and breaking those tables down in normalization and ideas like this. That's a type of technology which says, I want to make sure that my data is stored efficiently for the size on disk. I want to take those duplications of pieces of information and store them just once. And then I'll use compute in the future to stitch that data back together in order to bring back the master set. Now, that in the world of the cloud is slightly problematic because... Pause.
Sorry, you need to switch mics.
I need to switch mics.
Sound guy is giving you... Well, the mic is destroying that.
Okay.
Sorry.
Okay.
Hang on, guys. Try it. It's on.
Hello? Hello? Can you hear? Okay.
Right.
Can they hear at home? Who knows?
Who knows? We'll try it out.
Oh, and a bottle of rum. Okay. Okay, so we've had a few Santa Claus jokes, and we've tried to change my microphone. Hopefully everything will go well from here. So what was I saying about SQL Server? Yes, so it breaks the set of data down to reduce duplication. That's one of the primary reasons to have a SQL Server through this thing called normalization. And then you trade off that saving of storage space and capacity with a later expense of rejoining that computationally by using CPU. Now, that is not a valid modern approach because joins are expressing that you need to rejoin information. You need to take pieces of data and put them back together because you've stored them independently for your performance on the hard drive. Now, the problem with that these days is that the storage capacity itself is incredibly cheap, orders of magnitude cheaper than actually reusing compute in the future to stick things back together again. So that sort of approach has led us along the lines of NoSQL databases and document stores where we can hold information together in a non-relational way and make sure that we can express an intent of our query which says something like, give me back everything that represents Andy, and it just gets you back a whole document, and we don't have to do anything with compute, we just have to store it a little bit more verbosely on disk at any point in time. And finally, this is how our brains work. We think about data as points, we don't think about them as tables. We think about things like, Andy's got a friend called Alan, and Alan's got a friend called Magnus, although I'm not necessarily sure about that bit. Anyway, so, ooh, zing. Okay, so what I've expressed here is a graph of points of information about a couple of things, especially that Andy uses a technology called Neo4j. We'll get on to a bit more about how he uses that later on. And Neo4j is made by a company called Neo Technologies who were formed here in Sweden. And you can see that Sweden also has a few other pieces of information attached to it, that Magnus was born here, and Alan lives here, and ABBA was formed here. So what we've done is we've managed to equate databases with a pop band. So we can do that because our brains can do that, because we can go, Sweden, what's great about Sweden? Neo Technologies and ABBA. Our brains can do that, and therefore our databases should be able to too. And really that comes down to two things. One about storage, one about ability to query, and then at the same time, ability to model. So we want to be able to query our database in a way where we say we're going to start at a certain point where we don't actually have to go across an entire database just to get one thing back. We want to start partway through a table. And we also want to be able to say, I want to design the system so it matches exactly how I want to express my logic over the top of it. The technologies we're going to look at are going to be mainly Java, and they're going to be mainly sort of things that aren't necessarily Microsoft focused technologies. But Every example I'm going to show, apart from the very first one, is going to be in .NET and in C# at that. And that's because the world of our technology is becoming more open, and people are implementing things like REST services that have become well documented, and people out there are supporting that in multiple SDKs that come primarily from the open source community. Final point, as I mentioned it before, is that you shouldn't be worried about running a large Java estate. You shouldn't be worried about having 1,000 nodes or instances of Windows Azure of Ubuntu, because even though you might not know how to tweak it to get the best performance, if your intent is to run a query, then you run your cause, you execute your query, and then rather than worrying about tuning it and cleaning up its disk for future use, you just delete the entire thing and that's it. You don't have to worry about its maintenance anymore. So one of the ideas here, which comes from the DevOps world and also from this commoditized query idea about business, is that we don't have to maintain estates that are problematic for our business to maintain. We just let the cloud do that, provision it for us, and then delete them rather than have to maintain them. So let's get on to some technology. First up, the elephant in the room all the time, it's Hadoop. Hadoop is an open source distributed compute framework. It's maintained by the Apache Foundation, and there are quite a few distros out there of third-party companies that have taken it and given it a certain flavor. So it might be a flavor which works better with Windows or with a particular type of Linux. It's written in Java, and it effectively is a MapReduce framework for job delivery and a distributed file system for file access. What that means is MapReduce is a two-stage programmatic paradigm where we start saying, first of all, I get my data into a map class and a map method, and I select the things from that which are relevant and important to me, and I group them and pass them all together to a second phase called reduce. And that reduce phase then works out some kind of aggregated value from the master set. The distributed framework for compute is that you give it a job, and a job describes things like which classes are doing which part of the work, and you tell it how many nodes you have in your cluster and where they are, and it will break down that job into tasks and distribute those tasks to individual nodes where the work is actually undertaken. At the end of that process, the information is passed back up to the job level, and the aggregated results are either passed again into a reduce phase, or they're returned to the end user. In Windows Azure, we have a service available, which is now in public beta or public preview, I'm not quite sure the name of it, but you can use it, and my company, Elasticloud, have run the world's largest instance of this, which was over 500 cores, and that was very, very performant and didn't cause us any problems, any more problems than it would have done if it was 5 cores, so it's a very mature provisioning cluster. And what the HD Insight gives you, I like to think of it as like an MSI that works in the cloud, so like a Microsoft installer sort of file. And what it does is it puts all dependencies onto the machine, it configures it to work together, it finds out where the data nodes are that it's building at the same time and where the head node's going to be, and it starts plugging together all the things that are necessary for it to work. And it all happens automatically for you. So at the end of the provisioning cycle, when you said, I want one of those services, please, Microsoft, and 20 minutes later it's given you one with 500 cores in there, everything can communicate with everything else. It's all set up perfectly. So who's familiar with the big O notation? Okay, so quite a few. That's good. So this is old school computer science, old school to me. That's still actually relevant. It just sort of takes me back to my university days, that's all. It's a way of describing time complexity over data set size, roughly. So that's like saying, if you're going to, say, run over a petabyte of data, and then run over 10 petabytes of data, how does it compare? What's the gradient? What's the relationship of time expense that you need when you go between those two data points? Now, Hadoop is ON, big ON, which means that it's linearly performant. It literally doubles the amount of time taken as your data set size doubles. That's probably one of the worst, although there is OM log n, which is slightly worse, but it means it's fundamentally inefficient. It doesn't do anything to your data to make it more performant as you exercise things. So it simply stays the same performance level at all points in time. Double the data, double the time. Now, that is because Hadoop fits into this category of database technology called batch and called brute force analytics. It has to go over every single file that exists in your set of files, and it has to go over every single line that exists in every single one of those files every time you tell it to do a command. So it can't go just and look at yesterday's data and give you a result over everything else. It can't cache the result it did yesterday and add that in. You say to Hadoop, go and get me all this information, go and work out this query over my set of data. It has to go back right to the start of time and go over every single line there. Now you can be clever, of course, and you can start caching the outputs of results and then making vectors on those results yourself, but that's not part of Hadoop. If you want to do a query over an entire data set, there is no sort of incremental processing to it. So that makes it an ON process. Let's look at some scary Java. It's not that scary. It's a little bit scary. Just to point out, this is JetBrains IntelliJ, which makes Java coding almost like using Visual Studio, because all the stuff I like in Visual Studio comes from ReSharper anyway. So I'm sort of like using ReSharper for Java here, and it just sort of like makes my life really easy. It understands things. So what we've got here is a simple MapReduce job in Java. You have to define configuration settings. You have to give it an entry point with a main method. You have to tell it what it's going to run in this configure method. And then, if you scroll down that file a little bit, you get down to the actual core of what happens. You have a map class, and then you have a reduce class, and they both inherit or extend from a particular base class, and they implement a particular type of interface. And that's telling Hadoop how it can communicate with these bits and pieces. Okay, well that's Java. Let's pass that out of the way. So I won't dwell on that too much, because I've got beer coming later. If you want to ask me about Java, ask me when I've got a beer in my hand. But let's look at it from the C# point of view, because that's going to make a lot more sense. First of all, you go into Visual Studio, and you pop open NuGet Package Manager, and it would you type in Microsoft Hadoop in the top search box, and it will filter down to these 4 reference packages that you can import. The first one is the integration one. It's called Microsoft.NET Reduce API, MapReduce API for Hadoop. That gives you the base classes that you then implement and derive from. And the second one is a remote data and jobs management one called the Microsoft.NET API for Hadoop Web Client, which lets you sort of say, I'm here, the cloud's over in Ireland or in Amsterdam, I want to run a job, send a message up there to actually go and do all that stuff, and not have to do anything with remote desktop or get in communication low level with that machine myself. It just all does it through web services. The third one is Hive. It's a link provider for Hive, where Hive is like a SQL-like environment for querying of MapReduce. And this is a link provider which allows us to write link queries which are then implemented into a MapReduce job. And the final one is serialization. Avro is a framework where we can exchange information between different parts of the Hadoop ecosystem in a way that's well understood across the Hadoop ecosystem. So Avro is a bit like protobuf. It's a little bit like annotated BSON. So in terms of you saw what a file looks like, it's a bit like BSON, but it's got annotations on types. But we're going to look most of all at the very first of those NuGet packages, which is the MapReduce API. What it gives you are some classes that you can derive from. The Hadoop job is the primary one, and that's how you explain to Hadoop what you want this cluster of machines to work on at any point in time. And it has a single method that you have to override, and that's called configure. There are also some virtual methods that you can, like tidy up sort of methods, clean up methods you can implement as well if you want to. But all you have to do as an absolute minimum to get a job to work is tell Hadoop where your data is that you want to parse, that's the input path, and where you want the results to go to on the output path. So that's all you have to do in that method. But if you notice the derivation of this class, Swedish Sessions job, it derives from a Hadoop job which has generic parameters. And those generic parameters are going to be used by this API to work out what the map phase should be executing and what the reduce phase should be executing. So those two class names will be used at runtime to select a class to do our actual calculations. So let's look at the first one of those now, which is the Swedish Sessions mapper. And you can see here that all you have to do in there, derive from mapper base, which gives you an abstract method you need to implement called map. When you provide that implementation, it has a signature of the input line that you're parsing and a context, which is how you can talk back to Hadoop. Now, that input line is literally one line of that file which it's been read by Hadoop. You can configure how it's reading that, so you can configure things called file input formats, and input formats, which allow you to read different types of data like sequence files and things like this. But in the C# world, this is the sort of easy way and the standard way of actually consuming those files held on your cluster. And that is to give an input line per line into this function, which we call at runtime. And then we can just do string manipulation on that line. So we can say, if the input line contains this tag, country equals Sweden, in my case it's completely arbitrary, it could be something completely different, then we increment a counter, which is a way of telling Hadoop how far we are through our process, and we emit a key value. The key is going to be the Swedish country code, and 1 is going to be our value. Now, the interesting thing here is that this emit key value is actually absolutely at the core of how Hadoop is going to work, because anything where you find country equals Sweden on the line is going to go through into this block and emit the same key value. It's going to emit Sweden and it's going to emit 1. What's going to happen next is that all of those Swedens and 1s are going to get pushed together into one collection of things which had the same key. And that's what our reduce phase gets. So our reducer combiner base, which is the derived parent class of this, has this abstract method called reduce. Now, on there we have a single key, which in our case will be SE, and we have an enumerable of strings called values. So that's every single time in our system we're just emitting 1 over and over again. But they'll come in here as one collection, everything which matched that key of SE. And then we'll emit the count of those. We could also sum them, but we'd have to parse them into an int as well, because they're going to come through as string representations of the number 1. Okay, that's 101 on Hadoop and how you write it in C#. Now, one of the things I think Microsoft really excelled at in this space is bringing a framework in called Streaming Unit, which allows us to simulate or emulate the Hadoop workflow. So it's a little bit unusual, the workflow. There are classes implemented or instantiated for us that we don't have any control over, and they pass data between them. One gets the raw information, then it gets emitted by keys and values, and then it gets aggregated, and then it comes into our final conclusion. Now, to try and replicate that ourselves, we have to have multiple instances. We have to try and second guess what Hadoop is going to be doing at any of these points in time. So Microsoft have produced this streaming unit library, which is part of the first NuGet package I showed you, the Microsoft Hadoop API for MapReduce. And what you can say is, here's an array of input lines, and pass all of these into my mapper and then into my reducer, and then give me the results as Hadoop will make them. And because you're emulating that, you can step through this in Visual Studio. You can actually get real-time step-throughs of all of your classes. So here you can see that we're actually asserting the result of the very first result from the reducer is matching this strange SE tab 1, and that's because Hadoop emits things as key values by tab separating things. It is based among strings fundamentally. Okay, so what's important about this is that you can express your solutions in C#. Microsoft is doing a really great job of actually bringing the C# and the .NET developers into this fold. Your development team, if you've got a team of developers where you work, they can reuse their existing skills in a new space. You don't have to be scared about having to write that Java that we saw at the front. It's okay. You don't have to get scared about that. You can bring your unit testing through, everything you've learned about unit testing and how you can express intent repeatedly and make sure that you're always matching that. You can bring that through and make this a process which you don't have to rely on a 500 cores machine to tell you something's wrong. You can do it on one machine during your development time. And the other thing as well is that a lot of people out there will have the same experience as me, I'm sure, which is that you try to write a query in SQL Server and you try to express something programmatic, and you've sort of gone down this path of maybe using a cursor or maybe doing something like that, something which is really expressing programmatic intent over a set-based language, and it becomes very complicated, and then your DBA will come and start slapping you because you've used a cursor, and that's not a great thing. So the benefit that I see from this is that the programmatic way of expressing information, like an expression, is very terse, it's very short. It's why programming was invented, to get logic down out of our brains and onto a machine. Now, that's not the same as what set-based theory is there to do, which is to sort of do aggregates over sets of information. Now, with Hadoop, we're dealing with unstructured data or semi-structured data. It's all very fluid and difficult to react to. In the programming language world, that's not a problem. We just take an input line and we just do all kinds of parsing. Has it got this key? Has it got that key? We don't even have to worry about tables and columns and things like that. In other worlds, you do. I think that's one of the biggest benefits of using a modern programming language in the Hadoop world. And finally, I've harped on about this a couple of times, and that is this idea of the commoditized query. It's really core to why the cloud is very relevant in this space. And that is because what we can do is we can provision a set of machines, a HD Insight cluster, say, and we can pay for the compute that is there during the time of execution. And then we can deprovision that set of machines, and we can continue getting value from the work that was expressed within the execution time. So that means we pay for our actions, we pay for the amount of time that we have a cluster running. We don't necessarily, oh, that's fun. Okay, excuse me. There we go. Hooray! Excuse me. Okay, so we only pay for our compute when it's running, and then we have the value of what we worked out with our compute afterwards available for us. So what we can do is we can say, to run this query in the cloud costs us exactly $30. And that's because we know exactly how long it's going to take us to run, and we know that as soon as it's completed, we can turn off that cluster and stop paying. So if we know exactly how much we're going to pay to run this query, we can start making business decisions as to whether it's worthwhile running it. Now compare that to on-premises infrastructure, racks that you have to pay for over and over again every time they run out of life, but you don't actually even get the ability to say, running for this length of time costs me that much money. You can make a rough calculation, but it's not the same as what you get in the cloud, which is a fixed bill on the amount of compute that you've used. Okay, so why HD Insight, why Hadoop? HD Insight is great because of its automatic provisioning and job execution services. The clusters being transient, only being running for the duration of your query, means you don't have to worry about the state so much. There's this thing inside Hadoop, which I haven't really, inside the HD Insight, which I haven't really alluded to very much, but it's called the Azure Storage Vault, ASV. And what it allows you to do is put your information centrally. So if you're provisioning clusters and then deprovisioning clusters over and over again, and you're storing information on the hard drives of those clusters, well, that means those hard drives are going to get deleted. As the images get deleted, you're going to lose your data. It becomes relevant and important that you centralize your information, centralize your data. So in HD Insight, you have the ability to put that onto this thing called ASV. It's a HDFS proxy, which sits over the top of Windows Azure Blob Storage. So you address it as you would address any file in Hadoop, but you give it a different prefix, like a scheme, ASV : //. And because you've done that, rather than going to the disk on an individual machine, it reaches out to Windows Azure Blob Storage and gets the data from there. There's a similar thing for Hive. Hive is this way of expressing SQL type queries over the top of MapReduce. So you write SQL, select star from my table, and it goes out and generates Java, which then goes and runs on your MapReduce cluster. Now, that's great. One of the things you have to do there is define what your table is. So you have to say create table, give it a schema so that those files can work. And that means that one of the important things when, again, you're provisioning and deprovisioning your clusters is that you don't lose this metastore, because then you would lose the ability to query over the top of it, because querying is related to this metastore. What columns have I got? What tables do I have? So just similarly as ASV exists for the HDFS proxy, there's a SQL database behind which you can configure for the Hive metastore, which makes it centralized and makes it persistent between cluster provisioning. Additionally, there's a JavaScript console which you can interact with your clusters as it's provisioned. I would show you a demo of this, but demo cards being what they are. and time constraints, I imagine that would all go terribly wrong anyway. So basically, it's a JavaScript console which you can go into and you can say, list everything which is on my file system in the cloud, show me what's running, monitor the health of my estate, upload new files, download results, things like that. It's a console which gives you access to the fundamental workings of your Hadoop cluster. Right, so now we're over half the way through and a third the way through the content, as I like to be, just before the beers. And so we'll race through some examples of a document database, and particularly the one I've chosen is MongoDB. So, what is a document database? A document database takes something like a relational database that we might be familiar with, where we're storing people's contact information, their names, their addresses, bringing it together with a join on a person who has a name, so we can dedupe all of this stuff. And it takes that and puts it on individual documents. These documents then actually contain all the information about that person at any point in time. And that means that we can easily access that information at runtime. We can query and say, get me all the information about this person, and it returns me a document which relates to that person. We don't have to say, go and get me that person's information, and it goes, okay, I'll select this bit from this table, and this bit from that table, and this bit from that table, and this bit from that table, and I'll use a bit of compute to stick it all together and pass it back to the end user. The relational approach to this makes it very, very difficult to scale out because we're having to use compute at any point along that hierarchy. We have to keep using our CPU capacity that we're paying for orders of magnitude more than we are paying for our storage. We have to use that compute to actually stitch that information back together. So that becomes expensive. It means we have to scale things out much further than we otherwise would need to. And it means that it's not a very efficient model for the cloud. There are some other advantages to document DBs as well. This is a sort of full version of document database where he has a name. This document's got a name, it's got a company, it's got an address, and it's got some contact details. But if you happen to be from Blackpool, as I am, or was originally, you might want to hide the fact that which part of Blackpool you're from because it's a little bit shady in parts. So you might have a document which actually only expresses his hometown and his name and nothing else. And you might have a friend or someone who likes to talk about how they've been published in lots of books and things. So they might like that on their document instead, rather than having information about where they live so you can send him letters saying his books are rubbish. And finally, you might have another friend who likes a really, really bad football team. And he likes them so much that he even wants to store his icons, his imagery, as part of his documents, because he's going to keep pulling that all the time. Even though I pay this guy good money to work for me, all he does, and I know he's watching, all he does is sit there on his emails, on Tottenham Hotspur feeds in his emails. Who even uses emails for that? It's got Twitter, man. Anyway, yes. Anyway, carry on with the talk. So the key facts about MongoDB. It's a so-called operational database. That means we can make queries of it. That's something you can't do with Hadoop. Hadoop, you have to go back to every single file and say, I want to parse a little bit of information about something. I want to go over every single line, every single one of those files. With Mongo, you can say, get me a bit of information, and it will just do that one thing. It will just select you one file back, one document back. It's got a really nice .NET wrapper around it, provided by Tengen, the company now called MongoDB Inc., by the way, who write the database. It helps you very well with schematically free and workloads where you're ever changing the shape of your data, so like semi-structured workflow. And it has a few things in it which make it great for the cloud. It's got high performance built in as one of its key tenets. It has the ability to use Lucene indexes over its inner workings to give you very quick querying over things. It has built-in replication failover, high availability, and sharding built in from day one. So that sharding, anyone who watched the earlier videos, if you didn't watch the earlier videos, don't ask. So the sharding is like a first-class citizen in MongoDB rather than something that's been bolted on after, which allows us to have scalability as a first-class citizen in the system. So let's have a look at some, before we get on to the code, back to O notation. MongoDB can be explained as being big O log n. So that means that because it has some forms of indexing in there, it does touch your data, it does put it into indexes so you can query it quicker over time. As the data set doubles, the time increases by a fixed amount, because at some point you're going to need to start including network topology changes to scale out. However, with the ability to do indexing over the top, that is decreased from a linear model like we would have seen with Hadoop. So quickly through the strengths, there's a great .NET SDK, which I'll show you in a sec. It works really well with as an operational store. And when you get to the point where you've got a lot of data, but you don't necessarily need to go to Hadoop because you're making maybe domain model queries which are very well understood and maybe don't show too much variance, too much programmatic intent at the point of query, then you can build in this map reduce function, which is actually part of the MongoDB. And that means that you can get very similar type of programming experience as you would do with Hadoop. It's written in JavaScript rather than C#, so even when you're using the C# wrappers, you still have to embed a little bit of JavaScript in your C#, which is really ugly, but hey, maybe they'll fix that at some point. Now I've said it. It's designed for scalability. It's elastic is quite a key thing as well. So as you give it more nodes to work on, it can find those nodes. You can easily add them into a management system. In Hadoop, even though we say Hadoop is much better at scaling of this linear performance idea, one of the things about Hadoop is that you have to sort of stop all these daemons and restart all these daemons if you want it to then pick up new nodes that are in this topology. The other thing as well is that Mongo is free, even though Hadoop is also free, but this is like free in the same way that MySQL is. You can go to production with it, you don't have to pay for it. The tooling is not free. Typically, people who are involved in this ecosystem are making money off their tools, off their GUIs for managing the system and that sort of thing. Swings and roundabouts, but the database itself is free. Also, it's got a huge popularity. So if we go on to our next slide, this is what you get when you type in MongoDB in NuGet. You get 5 pages of stuff. And the first one is the official one. That's the one I recommend you have a look into first of all. But there are other ones in there. There are things which wrap the official release for the SDK of consuming Mongo through a C# application. And they wrap it in a way which might fit another programming paradigm. So this one on the first page is a repository pattern around Mongo. So you set up your repositories like you would do if you're familiar with EF, that sort of idea. Then there are alternatives. So people out there have tried to augment the way that the open source MongoDB driver is written, tried to change it, tried to make it more suitable to a type of programming or an approach, or plug it into something that already exists, like an ORM sort of idea. And that means that there are lots of alternatives to explore as well. If you find a problem with the official driver, you can move on to one of the other ones. There are also tools that you can get on the first page. So if your data is regularly structured, this is a structured data set, something that you might be comfortable putting into something like SQL Server, then you can get a collection. So a collection is equivalent to a table. So it's sort of the same level of stuff. It's a group of things which relate to each other. They're the same thing, but they're not got the same structure or format. It's just things that you can go to and say, everything in this collection is the same sort of entity. So in our case here, what we've got is we get a collection, and then we insert a buck into that collection. We just create a plain old CLR object, and we call bucks.insert, and you pass it that object, and it goes and creates a representative version of that straight in the database itself. If you don't have a structured data set, you've got an irregularly semi-structured data set, you can use the Beeson document approach, where you create this Beeson document which gives you effectively a name value pair dictionary sort of idea, and you just keep putting items onto that. And so you can have child documents within the parent document. You can express it in this way. And again, you just get the collection and you insert, this time it's a person, into the database. Very simple programming model. Its real strong points are that semi-structured data are a first-class citizen, just as we heard before about Windows Azure table storage. but it has built-in MapReduce. It's operational, it's interactive, it's cheap, and it's massively scalable. So if these are things you're looking to succeed with your data structure, I'd look at this as well as a fully featured database alternative. Okay, now we're going on to the last third of the talk, which is about graph databases. And the examples I'm going to show you are from a graph database called Neo4j. So a graph database has the ability to store documents, which are called nodes. And more than that, it brings in the idea that you're familiar with in the relational world of relations. But they're a little bit different because they're not relations that work across entire tables. What they are if you take a document, which is a node, and another node, and you draw a relation between them, you can then tag that as a type of relation and with properties on that relation, which say that Andy likes Magnus quite a bit, but Magnus doesn't like Alan, not very much at all. Just to go back to that old zing at the start. I don't know why I'm trying to fight over here, I don't know. Maybe I'll start picking on you two next. Glutton for punishment. So the nodes themselves can also have properties, and the relations between those nodes can have properties. So if you've got a data structure, which is, like we saw before, a person which has an address, you might have a document, a node which has got the properties of who the person is. And then you might have another node which is the address, and then you might draw a relationship between those two objects and say it's the type, lives there, or was born in, or something like that. So this technology, Neo4j, is open sourced by Neo Technologies, originally formed in Sweden. So congratulations, Swedish guys. You're in the same country as them. I don't know what that means. It's written in Java. It's Java, so it runs well on multiple platforms. It runs equally well in Windows Azure, on Windows VMs, or Linux VMs as well. There is a VM depot. Who here has heard of the Windows Azure VM depot? A few people. Good. So for those of you who haven't, it's an open source repository of images that you can, with a single command, put into your Windows Azure subscription. So there are images out there for a whole heap of different things. It's part of MS OpenTech. So go to vmdepot.msopentech.com and have a look at what's available. It's all the stuff that you ever wanted to do that isn't officially supported by Microsoft and someone else has gone off their own back and done it, but you don't have to then re-implement it like you would if you nicked it off someone's blog. You can just go, give me that literal image in my subscription and let me use it. It's an amazing place. And there is a hardened, which means configured with firewalls and stuff like that, Neo4j image in the VM depot. There's a open source .NET SDK as well, which you can get on NuGet, and it's maintained by an Australian company, Redify. Now, important bit, big O notation one more time, last one. Neo4j's O1, which is the effectively perfect time constant performance thing that we're looking for if we want highly performant systems. So that the algorithms inside a certain query will take the same time to execute irrespective of the size of the data set. That means that we can have a very huge data set, and if we have a certain well-known number of relations from point A to point B, and that number of relations doesn't change, then we can get constant performance even if the rest of the data set blossoms out. That doesn't necessarily mean you can do everything really, really quickly, because if you look at the number of relations that you're trying to traverse, and you suddenly go from one relation from Andy and Andy's friends to Andy and Andy's friends and their friends and their friends and their friends, that query might still touch your entire graph. All of the nodes in your database might be touched by that, so that might mean that your performance over time degrades because you're touching every part of your graph, and that, therefore you're doing compute over everything. Okay. How this is achieved is because of this concept called a start point within the document data, the graph database. And that means an index or a way of addressing an individual node at a point within the graph. And you can go straight to that point in the graph, and by using this thing called adjacency and adjacency lists, you can look at everything that that particular node relates to. And because the database is engineered in such a way that adjacency is an efficient operation, That means we can go to a start point on the graph, select everything that it relates to, and bring them back in a very efficient way. From that point as well, we can traverse over the graph in a variety of different ways. So one of the really important things about graph databases is they're modeled on these nodes or data points and relations to other data points. It's exactly the same process as our cognitive process. And we can actually start to map out things really quickly. So if you've ever worked with a business analyst who's sort of gone, right, I want the system to work like this, and they started drawing things. What they draw is like a node. They go, customer has shopping bags, has account, has, you know, some kind of credit card, something like that. I know that's this. And good impression of BA, right? Exactly. So, so the nodes themselves are exactly as people think they are, and the relations around them are a natural path to get computational logic out of actual people's minds. Now, that's really important because one of the biggest problems we have with data is we tend to look at data as something that we need to put into a system. We need to sort of, data's a problem, data's difficult, we're going to do something with this data that makes us query it. Well, really it's not. What our problem is expressing our intent over the top of that, and if we start thinking about things that it has to fit into a table, we guarantee that it's going to fit into a table rather than actually do what the system's meant to do, which is express intent over queryability. So, back to our equating database technologies with pop bands. This is a sort of graph that we can draw in a database, and this is how you actually end up with your mind map as well. So you start saying this person relates to that person, this person likes this thing, who build that thing, and this is effectively where you get to. Now, when you start looking at writing code for that, you want to start doing things like expressing, starting at this country called Sweden, which we're going to look up from a node country index. So that's an index node called country index. And we're going to give that a particular search term within the index. So starting at that point, match anything which has the relationship to Sweden, which was formed in something. So this is a little bit of ASCII art, which says that we want to return something which has the relationship to Sweden formed in. So that would be Neotechnologies, and it would be ABBA. If we want to do something like find friends of friends, this is a very common query that we want to do with social network types of workload, of data workload. And you really, really don't want to be doing like nested queries in something like SQL Server because the performance hit that's going to have. So instead, you can see very easily how easy it is to traverse these relationships. So you start at this node from the people index called Magnus, and you want to say, right, I've got Magnus. Now match the people who have a relationship from Magnus to someone called friends. I'm going to call that entity a friend. And from that friend, I want to then traverse to anything which has got a relationship which is a friend. And that is a friend of friend. And then you can return just the set of friend of friends. You can also do some really interesting things about shortest paths between objects. So you can say, start with Andy and find the shortest path to ABBA, and then work out whether it's going via Alan and his friendship with Magnus, or whether it's going to Neotechnology being founded in Sweden, where also ABBA was founded. So it's an interesting type of analytics that you can do built into the framework. Now, how do we consume this in C#? So we go to NuGet Package Manager, and we type in Neo4j, and it'll pop up with this one by Tate Modi and the guys over at Redify, and it's called the Neo4j client. And we install that into our C# application. Then we get the ability to express Cypher as a fluent style of programming. Those queries that I was showing before, start at this person, is a language called Cypher, and it's effectively T-SQL for this graph database. And what we do here is we say, get a Neo4j client, then in Cypher, start at this point called Sweden, which is by an index lookup on the country index with the name value of country in Sweden, and then match and express this ASCII art style of expression, and then return strongly typed nodes of those friends, given the alias friend of friend. So we can do this And in, what's that, 4 lines of C# code, we can actually write cipher queries which go out and start traversing friends of friends relationships within the database. We don't have to do anything clever with our database either. We're just using node A has a relationship of friend to node B. And then at some point later, we can start tagging things like node B has got a relationship of friend to node C and node D. And we can build this up over time to build a social graph within our systems. So if anyone out there has been faced or is facing the challenge of expressing social networking type queries, well, what you have to do is build a graph in a graph database like that. So yeah, okay, so that's a question. The question was, is Neo4j smart enough to do symmetric relations? So that would be not going around in a circle forever in terms of getting to, okay, yes. So you have 2 main types of graph database. One is a cyclic and one's an acyclic type. Neo4j is a cyclic type, which means you can go through that relationship, but you won't ever get into a recursive pattern. You can happily say this, and it won't then leap between those points. It's a good question, thanks. So we just go quickly over the things that graph databases bring to the equation. They are model domains of data which match our cognitive process. They're optimized for traversal of relationships, so we no longer have to have document databases which say parent document, child document, a binary relationship. It has one or it doesn't. And we don't have something like a SQL estate where we have table relates to other table, and if it has an entity on the right-hand side, then it's got a relation. If it doesn't, it doesn't. Again, a binary relationship. We can have very colorful relationships, which can even have weights and properties on those relationships. So we can do things like match friends of friends where they have gone out together to watch football at some point. So you can actually start saying things in queries which are very powerful indeed. You can also have different types of relationships between the same nodes, so likes of friends of colleagues. The way that the database is written and engineered with this whole idea of adjacency and adjacency lists on nodes means that you get big O1 performance characteristics because you can start at any point on the graph that you can address. That doesn't necessarily mean you'll get constantly excellent performance, because if your graph goes too far out in terms of the number of relationships trying to pull back without filtering on those, you can touch your entire graph and there you can get performance issues. But otherwise, if you model correctly and you constrain your queries over a small, well, reasonable size graph traversal, you get much better performance with this type of database than you will with any of the others for this problem domain. Okay, summary. HD Insight brings Hadoop to Windows Azure. It does all of the old-fashioned big data challenges which people give the V's to. So volume, variety, variability, velocity, all that sort of stuff. MongoDB works similarly, but actually brings in operational concerns too. So you can run a website off MongoDB, you can't run a website off Hadoop. Neo4j brings graph databases to Windows Azure. Relationship traversal, social networking types of data structure, that's where it excels at. Okay, so that's me, that's the talk. Thanks very much for listening, and I hope there's some beers later, and maybe a question or two.